Hello, I'm Zohreh Davoudi from the University of Maryland. This is the second lecture on the topic of finite-volume formalism for Lattice QCD as part of the Lattice Gauge Theory for High Energy Physics traineeship course. So in this lecture, we're going to talk about quantum chromodynamics, or QCD, the theory of a strong force in a finite volume. This is going to be a shorter lecture compared to QED in a finite volume. We'll continue this lecture next time on the topic of multi-hadron physics in finite volume. But for today's lecture, we're going to talk about single hadron sector first. We will talk about general features of QCD in a finite volume with periodic boundary condition. And I'm going to talk about finite volume corrections to single hadron observables by focusing on the example of nucleon mass. And then I'm going to have an exercise for you all on how to calculate corrections to nucleon axial charge in lattice QCD calculations in a finite volume. Okay, so let's talk about the general features of QCD in a finite volume with periodic boundary conditions. So here we don't have issues with the propagation of massless modes anymore, just because despite the fact that we have massless gluons in QCD, the low energy degrees of freedom are really these confined hadrons. There is a mass cap. Whether or not these are mesons, baryons, or gluons, again, they have a finite mass, and therefore they're confined inside the volume of the system and cannot propagate freely to the boundaries, okay? So now we're going to see that this feature really makes it easy to understand and formulate finite volume corrections in QCD. And in particular, we don't really have to deal with redefining or reformulating QCD in a finite volume in a way that we had to do with QED. And again, the reason is there's no charged SU3 objects, quarks and gluons inside our boxes. Everything is confined into SU3 invariant objects with a finite mass gap. And therefore, we have to worry about the lightest hadron in the theory, which is the pion, because these are the ones that can actually have a longer Compton wavelength and be able to see the boundaries, okay? So, and another important point is that while QCD is a complicated theory, obviously it is not perturbative. That's why we're performing these sophisticated lattice QCD calculations to be able to learn properties of hadrons, right? So then the question is, how do we actually identify then finite volume corrections for QCD, given that we don't have those same perturbative tools that we had in our disposal in dealing with QED corrections, okay? The answer is simple. We're dealing with finite volume corrections that are IR physics, okay? And IR physics is rather simpler for QCD because, again, we're dealing with effective hadronic theories. So while the short distance physics is complicated, it's non-perturbative, that short distance physics is the same in a finite volume and in an infinite volume. And it is only the long distance physics that is going to affect the properties of observables in a finite volume, and we need to characterize those. And because of that, it really suffices to think about effective hadronic theories if we want to characterize the volume effects. Okay, so that's an important point, which is going to really enable us to deal with QCD finite volume effects in a very systematic way, it turned out. Another point is that things may not be as easy when it comes to single hadron physics. This notion of finite range of the interactions would allow us to characterize these volume corrections in exponential forms, as we will see. But again, even though the single hadrons have the finite Compton wavelength and it is we can confine them inside a box, for multi-hadron physics, if we're interested in dynamical observable scattering amplitudes, for example, then we have to deal with the notion of asymptotic states And those asymptotic states turned out to not be there for Euclidean calculations that we perform in lattice QCD. And also the finite volume physics is going to be very different from infinite volume physics. So then the question is, how do we deal with defining these multi-hadron observables when we have a finite Euclidean spacetime? That's going to be the topic of the lecture 3. So we're not going to talk about that at all for the present lecture, but something to keep in mind. That's why I'm singling out single hadron observables from multi-hadron observables. Today, we're going to just talk about the simplest but the important case of single hadron observables. Okay, so in order to understand how things work out, it's better to just work out an example. Okay, and the example would be nucleon mass. I could have looked at the pion mass as well, but because we dealt with pions previously in our effective field theory lectures more, I decided to look at the nucleon properties so that we get a bit more comfortable with also effective field theories of nucleons and how to perform calculations with these effective field theories for nucleon observables. Okay, so as I said, yes, nucleon is a complicated object in terms of quarks and gluons, but because I'm going to estimate finite volume corrections to the mass of a nucleon, I can think about IR physics and therefore a corresponding effective field theory that would describe the interactions of the nucleon with other hadrons in the theory. Okay, and we're going to work with chiral perturbation theory again. You've seen chiral perturbation theory before. We deal with Lagrangian as a systematic expansion in some expansion parameter, in this case, the momenta of the process over the breakdown scale of chiral perturbation theory, or m pi, the mass of the pion over the breakdown scale. Okay. So we could work with chiral perturbation theory. It turned out that, and we have seen the form of baryon interactions in chiral perturbation theory before. It turned out that it's much easier to work with another formulation of chiral perturbation theory called heavy baryon chiral perturbation theory, because the mass of the nucleon is a large number, right? It's comparable to the breakdown scale of the theory. And if you keep it in the computations, you have to always worry about this not being the mass scale that breaks your chiral perturbation theory, but rather another large number in the calculations that you have to worry about when you do your expansions. So it might be better to actually think about non-relativistic limits of these nucleons when we're dealing only with the kinetic energy of these nucleons as opposed to the contribution that come from their large rest mass. And that's really the formulation of heavy baryon chiral perturbation theory. In other words, we consider the momenta of these nucleons to have two contributions. One is the first term over here, which comes from the rest mass of the nucleons, this m n naught that I have here, times some momentum vector, because I need this Lorentz index over here. And this is really the velocity for vector, which in the rest frame is nothing but 1, 0, 0, 0. Okay, where 1 is the zeroth component of this velocity vector, and the rest are special components. In other words, in the rest frame, we want the nucleon mass to come out of this term. Okay, what is left is going to be some sort of residual momentum, and I'm calling it L mu or something else in the rest of this lecture. Okay, so this is sort of the notion. So then you go ahead, you look at your chiral Lagrangian for the nucleons, and you try to then write it in the form of sort of these new variables. And in particular, the kinetic operator is now going to just look like the d dot v, where v is the velocity vector that we defined before, and this is our derivative operator. And these are n bar n, the nucleonic fields. And then this is the mass term, and so on. Okay. So again, in this notation, a nucleon could be either a neutron or a proton. Okay, so let me identify this. So it could be a neutron or a proton, so an isospin doublet, but each of these guys could also be in a spin up or a spin down. So really there are 4 degrees of freedom that we have to consider when we think about this capital N object, right? So this is for the free part of the Lagrangian. Then what about the interacting part? Again, before we talked about this interactions in chiral perturbation theory between nucleons and pions, and those interactions are chirally invariant, and therefore some derivative of the pion fields is going to appear in those interactions. This is pretty much the same that we had before. This is an interaction is proportional to the axial charge of the nucleon. This pion decay constant f pi, and then we have the sigma and tau Pauli matrices, where sigma acts in the space of the spins, and the tau are a bunch of Pauli matrices that are acting on the space of isospin. Okay, and this is our derivative coupling that is coupled to the spin Pauli matrices, and this is the pi field that is coupled to this isospin Pauli matrices. Remember, the pions come in 3 different species: pi 0, pi plus, pi minus. You can write it as pi 0, pi 1, pi 2, and pi 3, and then couple it to these 3 isospin species of the pions. And then you have your nucleonic fields. Okay. So for all purposes, that's all we need. We need the kinetic part of the Lagrangian for the nucleons, and we need the leading order interactions between the nucleons and other objects in the theory. In this case, for chiral perturbation theory, that would be the pions. Okay, of course there would be other hadrons, but this is the dominant contributions for our purpose. All right, so let me erase these lines and then go to the next page. So then we have the Lagrangian. The next step is to identify the Feynman rules for the theory. So for the nucleons is going to be this form. Again, I look at the previous Lagrangian that we wrote down, and then you just read off for the free nucleons, and you just read off what the propagator should look like. You already see from this form that in the rest frame, when V is essentially vector 1, 0, 0, 0, this rest mass is going to cancel out the contribution from the mass from this momentum vector, and you're going to just get contribution from that residual small momentum. And so in that sense, this is really that heavy baryon chiral perturbation theory that I was talking about that would cancel out contribution from the mass in the expressions. So it turned out that there is another coupling in the chiral perturbation theory that I didn't write down. It's a constant. It's proportional to m pi squared. There is a coefficient in front of this that I've given the value of over here. For the purpose of our discussions, we have to keep track of it, but in terms of volume corrections to the mass of the nucleon, eventually, as we will see, it would cancel out. So it's not too important. This is the nucleon pion interaction vertex. It's got to be proportional to momentum because it's a derivative coupling. It's going to be proportional to GA over F pi. And there are these Pauli matrices in a spin and isospin that come out of reading of Feynman rules from the interaction Lagrangian that I wrote down before. Okay. Okay, so where I'm going with this is very similar to what we did in calculating the mass corrections to charged hadrons in QED in a finite volume. We argued that whenever we're interested in mass corrections or in principle, the contributions to the mass, they come from sort of radiative corrections or the corrections to the self-energy of these objects. And for a nucleon, the self-energy gets contributions from interactions with the pions. It can emit a pion, the pion can propagate, feel the boundaries, come back, get reabsorbed by our nucleon. And in the process, then the mass of the nucleon is going to be affected by those boundary effects because of the presence of these pions that can propagate. despite the case of QED, where photons can go all the way to the boundary because they're massless, in the case of pions, they have a limited range. So we're not going to see the same volume corrections out of this calculation compared to what we did in the QED case. Okay, so let's calculate this. Let's talk about the corrections to the nucleon mass, and I'm going to do this explicitly. This is what you have done in quantum field theory courses before, but because now this is a new formulation of baryons using this heavy baryon effective field theory approach, let's just be explicit and see how a self-energy can correct the baryon mass or baryon propagator. So the full propagator for our nucleon in this case is the leading order propagator that we had before out of our Feynman rules, but then it can get corrected by this one particle irreducible diagram, which is the sum of everything that can contribute inside, which is connected, and to this diagram with two nucleonic legs. The next correction is going to be two of these 1 pi contributions to the self-energy and so on, right? So then I write down explicitly what each of these bare propagators look like in this theory, which has the following form. And then in the process, you also factor out these 1 pi self-energy functions, all right? So now this is obviously a geometric sum. You can sum it up and you end up with I over this factor, right? And this factor now in the denominator has contribution from the self-energy. And I can equate this to a renormalized propagator where there's this z-pole renormalization, right? The renormalization factor. And the p dot v minus mn, where this nucleon mass is now the actual pole, the physical pole of the propagator, as opposed to the bare mass that we have in this expression here. So I'm just re-expressing this whole thing as this, right? All right, so then how do we make sure that this propagator has the pole at the physical mass? This is essentially by saying that I want this mn to be the pole of this object as well that I have equated this with. So this is really the condition. I want the PV to be equal to mn on this side, and therefore on the other side, that means that PV minus mn, the bare mass of the nucleon, minus the self-energy function, everything evaluated at the physical mass equal to P dot V should be equal to 0. That's the condition, okay? So that means that the physical mass should be equal to the bare mass plus the self-energy when it's evaluated at P dot V equal to the physical mass, okay? So this is very similar to what we've seen in quantum field theory for example, QED and other theories or QCD, but not in the language of this heavy baryon or heavy nucleon chiral perturbation theory, okay? But the ingredients are very similar. Okay, so now that we know how the mass gets modified by this self-energy, the task is to find out what the self-energy function looks like. And we can do this order by order in chiral perturbation theory. In particular, in leading order, we just have this contribution from this contact term, that is proportional to m pi squared. So I'm going to call this minus I sigma leading order. And then the next one is going to be a contribution from this radiative pion corrections, right? So again, you use your Feynman rules that we listed on the previous page. You have two propagators, one for the pion and one for the pion over here. So one for the pion over here and one for the nucleon over here. This is there are two of these vertices, so you get GA squared over F pi squared, obviously. And this is a derivative coupling, so that's why you get a factor of K squared out of each of these two sides of the vertex. You have to sum over the momenta inside, or integrate over the momenta inside the loop. I'm still in infinite volume. All right, so no finite volume calculation yet. This is infinite volume. And then you see this interesting factor of 3/2. In fact, exercise 7 would ask you to derive and justify the factor 3/2 k squared in the loop expression that we have above. And this should not be too hard, but just noting that the pi-nucleon coupling has a factor of tau dot pi, which kind of looks like this. So you should be able to justify where that factor of 3/2 comes from, okay? So let me raise these. Okay. Now let's take this function that we have over here, and it's an integration over 4 momenta. And I'm going to just take the integration over k0 for the time being, and just leave the integration over the special momenta to later. And this is what we've done here, all right? So you take the integrand over here, you identify its poles in the complex plane of the k momentum variable, or k0 momentum variable. There are going to be 3 of these poles, 2 associated with the pions, and this guy associated with the nucleon. All right, so you decide whether to close your contour upward or downward. In this case, I'm closing it downward. So you pick up 1 pole, and then you calculate the residue at that pole, and you just do the math with all the signs and I factors and everything correctly. Then you end up with the following form for the result of integration over k0. Okay, so then this is going to be an integral over 3 momentum vectors inside, and then you have the momentum vector s squared, special momentum vector s squared, and then special momentum vector s squared plus m pi s squared. Okay, so there's no notion of k naught left anymore. We dealt with it, and now everything is in terms of this 3 special momentum. Okay, good. So this is, again, everything in infinite volume so far. But as I said, I'm interested in correction to the nucleon mass due to a finite volume. All right. Okay, so let me erase this bit. All right, so what do we do if this theory would have been in a finite volume? In terms of calculations that we've done so far, it's pretty straightforward, right? Because I have a cubic, a special volume. I want to keep the time extent to be infinite. This is a good assumption. Usually we take the time to infinity first in our Euclidean calculations, and we derive quantities associated with a special volume, but there is no notion of finite time. That's sort of the reason that we make that assumption in most of these calculations. In any case, so if the special extent of these cubic volume is fixed to be L, then again, I have periodic boundary conditions. The momenta are going to be discretized as 2 pi over L times some integer momentum vector belonging to z cubed. And that's it. Then we take the self-energy, and I'm interested in the corrections, meaning that self-energy evaluated in a finite volume, my self-energy evaluated in an infinite volume, okay? So then that would be the self-energy leading order and difference, and the self-energy next leading order difference, and so on and so forth, right? So the first one is 0 because the leading order was really m pi squared, or the first contribution that we saw. But the next one is non-trivial, because the next one that comes from contributions from these loops, we simplified it all the way to a form like this. And we already see that if we're in a finite volume, there's going to be an finite sum, a discretized sum, as opposed to infinite volume integral, right? So that's the only difference, and therefore we have to keep track of this contribution and difference in this contribution over here. That's all I've done. That's the bit that we arrived at for infinite volume, which is subtracted. The finite volume part is a summation over these discrete values of momenta, right? So how do we deal with this? How do we take the difference in the sum and integral of an object like this? There is a very useful trick, the Poisson resummation formula. Let me state what that formula is. The formula would tell you that if you have a sum over discrete values of momenta like so, as we have in our example, times 1 over L cubed, and the sum is over any function of that momentum K. In fact, you can replace that with another sum over another integer m, okay, where m, again, is an integer vector, 3 vector. An integral over now k, where k is now a continuous version of that discrete k on the other side of this equality. Of the f function as a function of this continuous variable k now, times e to the minus I k continuous k dot m, which are these integer vectors, times l. Okay? There is very straightforward derivation for this Poisson summation formula. You can look up Wikipedia, for example, to find this if you haven't seen this before. But as I said, this is a very standard form, and it is a very powerful trick in many of these finite volume calculations. So it appears that I'm going to replace a sum with another sum and integral, and of course this exponential factor, and therefore it looks like more complicated. So a priori, it's not obvious why I'm going to do that. But as you can see, the reason I'm going to do that is that, well, you realize that the first term in this sum, which is, or at least one term in this sum, which is m equal to 0 term, is going to give you exactly the infinite volume integral. Because then m is equal to 0, this exponential factor would go away, right, for that case. And then you end up with just integral over fk d3k over 2 pi q. So that's exactly the infinite volume counterpart of the other side, if m vector is 0, 0, 0. So for any m that is not equal to 0, we characterize just the pure finite volume corrections, right? One term in that sum is finite volume corrections. In fact, if I do this trick, I can cancel out this with the m equal to 0 term of this sum. And what is left, which are all the summands with not m not equal to 0, are going to be purely finite volume corrections. So that's the trick that we're going to pull. All right, let me clean up the page. Go to the next page. Okay, so that's how the calculation goes. Once you do this trick, the m equal to 0 term already cancels the infinite volume term in that difference. What is left is the following. You have your fk function, which was k squared over k squared plus m pi squared, and a bunch of prefactors that I'm carrying over. And you have this exponential term, which is proportional to both in the exponent m and k vectors. Okay. So then how do we work this out? Simple math. I have some of the steps here. I have first take the cosine theta, the integration over the theta variable over here. Integration over the phi variable is trivial, so that's why you have a factor of 2 pi here. But because you have dependence on the theta variable, then you have to keep track of this polar angle integration. Then what you have is eventually the following integral, where integration is now over the momentum, the magnitude of the 3 momentum k, which I'm just for simplicity writing it at k. Okay, so k to the 4th means the magnitude of the special momentum k to the 4th, right? So this is just a simple form. All right, so then you just simplify it all the way, and that's what you get. Essentially, integral over k from minus infinity to infinity of just this one term, k cubed over k squared plus m pi squared. At this point, you can just, again, pull out the tricks from counter integration tricks and identify the poles of this integrand in the complex plane. It is going to be either I times m pi or minus I times m pi. I'm closing the counter upward and taking the residue and everything, and that gives you this form. Okay, so again, if it was too fast, you will have enough time to go through all these steps on your own and be able to justify this final result. Okay, and in particular, let me just write the first few terms of the sum, because the sum is still not performed, and I don't have sort of an analytic form for it here, but you're only interested in the first few terms because most of them are exponentially suppressed, right? Even the first term is suppressed, but with a smaller exponent. So the first term is going to be when the magnitude of this integer vector is 1. So you get e to the minus m pi l over L, right? But why do I have a factor of 6? Essentially because there are 6 of these vectors in a 3-dimensional space that have magnitude 1. Okay, so that's the degeneracy of those magnitude 1 vectors. Of course, then the next term is going to be something like e to the minus a square root of 2 m pi L over a square root of 2L, and so on, with the corresponding multiplicity factors. It already is good enough, because if you make sure that your L is much larger than 1 over m pi, you can exponentially suppress corrections to the mass of the nucleon due to being in a finite box. Okay, so then this is exactly delta sigma, because of a relation that we had between the mass and the sigma, is exactly equal to delta mn, which is the difference between finite and infinite volume masses of the nucleon. Okay, and exercise 8 is to explicitly write down the contributions up to e to the minus 2 m pi L, and then plot this function, this finite volume correction, as a function of m pi L for the range between 0 and 6. And the reason for this exercise is that I want you to see the power of exponential, right? See exactly what the size of these contributions are, what is the size of the next contributions that I have dropped from the sum compared to the first contributions for various values of m pi L, so that you can get a feel of what m pi L value you should have in a lattice calculation, such that, for example, the contribution to the mass of a nucleon is just 1%. If you're interested in more accuracy, hopefully less than 1%, what is the size of the volume that you need for that calculation, such that you can control this volume? And obviously, if you don't, you still have this sort of analytic effective field theory-based form that can inform your extrapolation, right? So you can either correct for these volume corrections or extrapolate away with these corrections and get even a much more precise number, even if you don't have a very large value of L, right, for these calculations. So let's kind of zoom back and understand what happened here. We have a nucleon, the nucleons, there is a cloud essentially associated with a nucleon, a pion cloud. And in the language of quantum field theory, a pion cloud are these all radiative corrections associated with the pions. And these pions have a finite Compton wavelength, but still the wave function is going to be interrupted by the boundary and be modified. But those modifications are going to be exponentially suppressed, because we're dealing with a gap theory with these pions having a finite mass. So this is very different from compared to QED. In fact, it is very similar to the QED M that I introduced before, when we introduced a finite photon mass, such that we can make the range of the QED interactions finite and define an IR regulated theory that way in a finite volume. In the case of QCD, these pions are essentially the carriers of nuclear or hadronic force, and they are finite range. So we don't have to worry about their regularizing the theory further. The theory is already IR regulated because of these pions, at least at low energies, right? Okay, so let me clean up this page. go to the next page. Okay, so we talked about this kind of interpretation and what the size of these corrections mean for our computations. And finally, really, the last exercise is to do similar calculations for different observables. I mean, you learn the basic steps that are involved in identifying finite volume corrections. And again, for any other observables, it would have been nice to have an effective field theory that describes the low energy interactions of these hadrons with other hadrons in the theory. It turned out that for many observables, we have these expansions in chiral division theory or in other effective field theories of nuclear physics. This example is considering the nucleon magnetic moment. So in this case, it means that you have to consider the interactions between nucleons and photons. So don't confuse this case with the case of QD in a finite volume. I'm not going to consider photons as degrees of freedom here. In order to characterize magnetic moments of the nucleon, I'm just assuming that there is an external classical background field that is really coupling to our nucleons. So we're not simulating these dynamical photons so that we have to worry about their finite volume corrections and how to regulate that kind of theory. Not at all. We're just interested in the corrections to the magnetic moment associated with the QCD being in a finite volume. Okay. So what that means is that you have to start from this Lagrangian that I've given here in terms of interactions of nucleons and the pions and the photons, okay, in these two terms. Write down the Feynman rules associated with these interactions, and then ask yourself what, at leading order, what are the contributions to the magnetic moment of the nucleon? And you will have to deal with a bunch of single loops that are going to be replaced by a bunch of sums as opposed to integrals over the momentum loops. I have given a little bit of more description of the problem, so hopefully that would be, you would be able to really follow this. And in the end, you should be able to see that the magnetic moments of the nucleon is corrected by delta mu, this value, which is proportional to, again, the axial charge of the nucleon squared over F pi squared. The mass of the pion times the mass of the nucleon, and importantly, another exponentially suppressed contribution. Okay, so this is the sum over all n values of this form. Again, you can take the first term in the sum, which is the magnitude m equal to 1, and so that the leading contribution is e to the minus m pi L for this magnetic moment. Okay, so again, another single hadron observable in a finite volume that gets exponential corrections proportional to the mass of the lightest meson in the theory, these pions times L. Okay, the same is true for the kaons, for the pion properties, and so on. And therefore, these forms, these finite volume forms, enabled by our understanding of chiral per division theory and other relevant effective field theories of hadronic physics, have been very useful in identifying volume corrections to these observables and being able to correct and extrapolate them away. All right. So that's really the lesson of this lecture. And in the next lecture, we're going to see what is different if we think about multi-hadron physics, scattering amplitudes, and defining multi-hadron observables in a finite volume. And we're going to see there are very dramatic differences between single hadron scenarios and multi-hadron scenarios.